We can use this information to solve a few examples. The first example that we're given says, what is the Earth's speed as it orbits the Sun if it has a radius of orbit, if its radius of orbit is 1.49 times 10 to the 8 kilometers, and it makes one complete revolution every 365.25 days, or once every year. So let's first write down what the information we're given. We know that there's a radius of 1.49 times 10 to the 8 kilometers. Kilometers is not the SI unit we want to use. We want to use meters. So this is going to be 1.49 times 10 to the 11 meters. The other thing we're given is the time it takes to one complete revolution in a year. So the period is 365.25 days. But remember, we want to find what it is in seconds. So to do that, we are going to multiply by 24 hours in a day times 60 minutes per hour times 60 seconds per minute. When we do that, the days cancel out, the hours cancel out, and the minutes cancel out. So what we're left with is 31,557,600 seconds. So the Earth the Earth goes around the Sun every 31,557,600 seconds. So our question wants to find what is the Earth's speed. So what is the Earth's centripetal velocity? That is going to be equal to the formula 2 pi r over t. We have all this information, so now all we're going to do is plug in and solve. 2 pi times our radius, 1.49 times 10 to the 11 meters. Remember, we're using meters, not kilometers. And divided by our period in seconds. 31,557,600 seconds. When you solve this, you're going to get an answer of 29,666 meters per second. Again, if it tells you to solve in kilometers per hour, you can do that as well. To do that, all you're going to do is multiply by 3.6, and you'll get an answer of 106,798 kilometers per hour. The next example that we have gives us a car traveling at 16 meters per second going around an unbanked curve in a road that has a radius of 112 meters. What is the centripetal acceleration of the car? So in this example above, we solved for centripetal velocity. Now we're going to solve for centripetal acceleration. The information we're given tells us the car is traveling at a speed of 16 meters per second. It's on an unbanked curve that has a radius of 112 meters. We want to solve what is its centripetal acceleration. So to do that, we're going to look at our formulas, and we know centripetal acceleration is equal to the speed squared divided by the radius. Again, we have both of those pieces of information. All we're going to do is plug in and solve. 16 meters per second squared divided by 112 meters. So our centripetal acceleration is going to be 2.29 meters per second squared. Now that we've talked about centripetal velocity and centripetal acceleration, we can now talk about centripetal force. So, Newton's second law of motion says, if an object is accelerating, it has a non-zero net force acting on it. All right, so in other words, your net force is in the same direction as acceleration. Remember, if there is no acceleration, your F net is 0. That goes back all the way to the first unit. If an object undergoing uniform circular motion is accelerating towards the center, there has to be a force acting on it towards the center. So it's going to be the same thing. Again, we had our centripetal velocity acts tangent to the circle, and towards the center of the circle, we had centripetal acceleration. But we're also going to have, or if our acceleration is towards the center of the circle, we're also going to have our centripetal force is acting towards the center of the circle. A force that causes a change in direction but not speed must act perpendicular to the direction of motion. In circular motion, the force vector always perpendicular to the velocity vector. So that's the same thing we have here. Our force vector is perpendicular to the velocity vector. They're at a 90-degree angle. Newton's second law also says acceleration and net force are in the same direction. That's the same as what I had set up there. You can see acceleration and force are going to be in the same direction. When it's centripetal, it's always acting towards the center of the circle. And again, this is called centripetal force. So centripetal force is actually a net force. It's not a unique or separate force responsible for circular motion. Rather, it's a generic term given to any force that acts towards the center of a circular path. The centripetal force could be the result of the force of friction, force of tension, force of gravity, or a combination of the forces. Again, centripetal force in circular motion is our net force. It's all the forces adding together or acting together give you your centripetal force. So the formulas you're given on your formula sheet are F net is equal to mass times acceleration. We've talked about that one for quite a while now. The other one we learned today is centripetal acceleration is equal to velocity squared, or speed squared, divided by the radius, which is also equal to 4 pi squared r over the period squared. These are both on the formula sheet. What's not on the formula sheet is what you need to know. So, since the centripetal force is the net force, we're going to take this first formula and we can go centripetal force is equal to the mass times the centripetal acceleration. This is a formula that we can use. We can also branch this formula off into two further formulas. We can go centripetal force is equal to mass times the acceleration or velocity squared over r. So mv squared over r. The other one we can use the centripetal acceleration from the second part of the formula. So centripetal force is equal to mass times the centripetal acceleration, 4 pi squared r over t squared. These two formulas are more common to what you're going to use, but they are not on the formula sheet. Not directly, at least. You can use the information given to you on the formula sheet to create the two new formulas. So let's solve a problem using centripetal force. In this example, Greg swings a 3.5 kilogram pail at 1.5 RPS. The pail is attached to a 2.05 meter rope. Our first part, or part A, wants us to determine the centripetal force acting on the pail. So if we're doing part A, let's first write out what we know. We know the mass of the pail is equal to 3.5 kilograms. We know there's a frequency of 1.5 RPS, or hertz. We know that there's a radius of the rope of 2.05 meters. We can now use our formula to see what we can find. So, centripetal force is equal to mass times centripetal acceleration. So we have mass, we have frequency, and we have the radius. So since we have the radius, let's put our formula in here as 4 pi squared r times m divided by t squared. So good, we know 4, we know pi, we know the radius, we know the mass, but we don't yet know the period. We can find the period using the frequency. Using the formula, the period is equal to 1 over the frequency. So that's 1 over 1.5 hertz. So our period is 0.66 repeated seconds. So now we have all the information we need to plug into the formula. 4 pi squared times the radius, 2.05 meters, times the mass, 3.5 kilograms, divided by the period, 0.6667 seconds squared. When you plug that all in, you're going to get a centripetal force of 637. Again, since it's a force, our units are going to be newtons. The second part of the question wants us to determine what is the speed of rotation. So our formula for this is the centripetal velocity is equal to 2 pi r over t. We look and we have all that information. We know the radius and we've already solved for the period. So our velocity is going to be 2 pi times 2.05 meters divided by our period, 0.6667 seconds, and that's going to give us an answer of 19.3 meters per second. If a question, for example, maybe something you get on your unit assignment, asks about the direction of these, are they traveling in the same direction? No, they wouldn't when it's centripetal. Remember, the direction of the force is always going to be to the center of the circle, and the velocity is going to be tangent to the circle. They are going to be perpendicular with each other or at 90 degrees with one another.